Good evening, everybody. So, we are in the practice assignment session for the course contents covered in week 4. So, let us begin. First question: the Fourier transform of an exponential signal f of t equal to e power minus at u of t, where a greater than 0 is dash. So you're finding the Fourier transform of e power minus at u of t where your a is greater than 0. Please attempt the question and tell the answer. So what is the formula to find the Fourier transform? So integral x of t e power minus j omega t dt, and your integral goes from minus infinity to infinity. So this is the formula for Fourier transform. Now your x of t is e power minus at into u of t. From what limits does u of t exist? So u of t exists only from 0 to infinity. So this integral goes to integral 0 to infinity e power minus at e power minus j omega t dt. Now we have to integrate it. So e power minus t into a plus j omega by minus of a plus j omega. Your limit is 0 to infinity. So you get the answer 1 by a plus j omega. So the answer is 1 by a plus j omega. Is this okay, guys? Okay. What is the Fourier transform of sine of t? So what is this function, the signal sine of t? So if this is t and this is sine of t, sine of t has value minus 1 for t less than 0, and it has value plus 1 for t greater than 0. So it is -1 for t less than or equal to 0, 1 for t greater than 0. This is your signal. Now you have to find the Fourier transform of this signal. So you can write the formula for Fourier transform, split the integrals based on the limits, and then try to get to the answer. Okay. So in your Fourier transform formula, we have sine of t. Sine of t, now we're splitting it into two integrals, one from -infinity to 0, sine of t is -1. From 0 to infinity, sine of t is just 1. So now we are solving these two integrals. For the first one, it is minus e power minus j omega t by j omega, minus j omega, limits from -infinity to 0. And for the second integral, it is e power minus j omega t by minus j omega, limit 0 to infinity. So 1 by j omega plus 1 by j omega, your answer is 2 by j omega. So the Fourier transform of sine of t is 2 by j omega. If the Fourier transform of x of t is capital X of j omega, then what is the Fourier transform of dx by dt? So you have x of t, the Fourier transform is capital X of j omega. Okay. Now you've differentiated x of t, dx of t by dt. What is this Fourier transform? Can you guys try this? Yes. The answer is j omega into x of j omega. Okay. So let us see how do we get to this answer. So we have taken the inverse Fourier transform expression. So x of t is 1 by 2 pi minus infinity to infinity capital X of j omega e power j omega t into d omega. Now we are differentiating this inverse Fourier transform equation. So dx by dt is 1 by 2 pi into d by dt of this right side expression. Now this d by dt, it holds, or it can be applied only to e power j omega t. So when you differentiate e power j omega t, what you get? E power j omega t into j omega. So we have 1 by 2 pi minus infinity to infinity j omega into x of j omega into e power j omega t d omega. So this is equal to dx of t by dt. So this is again a Fourier transform, inverse Fourier transform equation, wherein to get dx by dt, you have to invert j omega into x of j omega. Correct? So the answer is j omega into x of j omega. Is this clear, guys? Okay. What is the Fourier transform of sine of 3t by pi t? So we have to find the Fourier transform of sine of 3t by pi t. There's one important thing which you have to remember, guys. So when I have a signal which is limited in my time domain, okay, it's time limited. If I take the Fourier transform, this signal will be spread out in frequency. So time limited signal, if you take Fourier transform, it is spread out in frequency. What if I have a signal that is spread in time? What will be its Fourier transform? So it will be limited in frequency. So it's just the inverse of it. So we have to find the Fourier transform of sine of 3t by pi t. So here we are making use of the duality property of Fourier transform. Duality property. If I have small x of t, its Fourier transform is capital X of j omega. Now, if I have capital X of t, that is instead of j omega, I have t. Okay? If I have capital X of t, the Fourier transform for this will be 2 pi into small x of j omega. So this property is called as the duality property of Fourier transform. Let us see how we get this expression. So first we take the inverse Fourier transform expression. X of t is 1 by 2 pi minus infinity to infinity x of j omega e power j omega t into d omega. Now we take this 2 pi to the other side. So 2 pi into x of t is integral minus infinity to infinity x of j omega e power j omega t into d omega. Now first thing what we are doing is, instead of t we are writing it as minus t. So t is equal to minus t. So 2 pi into small x of minus t. Same way here also you have a minus that has come in. Next step, we are interchanging t and j omega. So if I do so, I will get 2 pi into small x of minus j omega equal to minus infinity to infinity capital X of t e power minus j omega t into dt. So this is our duality property now. So if I have capital X of t, its Fourier transform is 2 pi into small x of minus j omega. We are going to use this to find the answer. Now, in our previous week session, we noted that if you have x of t as 1 for mod t less than a rectangular function, its Fourier transform is something like this: 2 sine of a omega by omega. Now we have sine of 3t by pi t. So we are trying to use the duality property and we are finding the Fourier transform. So the Fourier transform of sine of 3t by pi t now becomes 1 for mod of omega less than 3. So here your a is equal to 3. So the answer is B, 1 for mod omega less than 3 and 0 otherwise. Can I move on to the next question? Okay. Which of these is the power spectral density of Brownian noise proportional to? So, if we have to find the power spectral density of S of t, it is mod square of Fourier transform of x of t. So, it is mod of S of j omega the whole square. Now, the Fourier transform of Brownian noise is S of j omega is 1 by j omega. Now, to find the power spectral density, we are doing mod square of 1 by j omega. So it is 1 by omega square. Now, what is omega? Omega is 2 pi f. Omega square will be 4 pi square f square. So if power spectral density is equal to 1 by omega square, what can it be proportional to? 1 by f square. So the answer is C, 1 by f square. Moving on. If capital X of j omega is the Fourier transform of a continuous time signal small x of t, what is the Fourier transform of x of 2 minus t plus x of minus 2 minus t? So how can I write x of 2 minus t as x of minus t minus 2? How can I write x of minus 2 minus t as x of minus t plus 2? So here you have to apply the time shifting and scaling property of Fourier transform. Can you guys try this? Okay. So let us understand the time shifting property of Fourier transform. The Fourier transform of x of t minus t naught is capital X of j omega into e power minus j omega t naught. So let us see how to get to this expression. So we are finding the Fourier transform of x of t minus t naught. So y of j omega is integral minus infinity to infinity x of t minus t naught into e power minus j omega t into dt. This t minus t naught, we are taking it as some variable u. What will happen to dt? It will just be du. So we are doing a variable change. So instead of t minus t naught, we are writing it as u. And your integrals limits are minus infinity to infinity. So this is not going to change. So it's again minus infinity to infinity x of u e power minus j into u plus t naught into omega into du. Here you can split this bracket into two terms. So this is independent of u. So this we can write it as some Fourier transform capital X of j omega into e power minus j omega into t naught. So the Fourier transform of x of t minus t naught is x of capital X of j omega into e power minus j omega t naught. This is the time shifting property of Fourier transform. In a similar way, we have the time scaling property. So if x of t Fourier transform is capital X of j omega, then the Fourier transform of x of at is 1 by mod of a into x of j omega by a. So if you have x of at, then you have 1 by mod of a x of j omega by a. So using the time shifting and time scaling property of Fourier transform, now we will write this. So here we are using the time shifting and time scaling property of Fourier transform. A is 1 here, so we will write 1 by mod of a x of j omega by a. So there, wherever you have omega, we are going to have minus. And then t naught is 2 here. So we have e power j2 omega by into x of j minus j omega by 1 plus e power minus j2 omega into capital X of minus j omega by 1. Now this capital X of minus j omega is common, and then you have e power j theta plus e power minus j theta by 2. This is basically cos, right? So these sum of exponential terms, with that you're going to get 2 into cos of 2 omega. So the answer is 2 into capital X of minus j omega into cos of 2 omega. So the answer is C. Is this clear, guys? Okay. A continuous time signal x of t which has a Fourier transform capital X of j omega is cos of 3 omega into sine of omega by 5 is dash. So the Fourier transform of x of t is given to you. With this, we are going to tell about x of t. What x of t is? Is it purely real and even function of time, or purely imaginary and even function of time, purely imaginary and odd function of time, or purely real and odd function of time? So with the help of Fourier transform, we are going to tell about x of t. So first let us understand what type of function is this Fourier transform. You have cos of 3 omega into sine of omega by 5. First, it's a product of cos and sine, so it is basically real. And cos is an even function. Sine is an odd function. What is the product of odd and even? Correct. So it is odd. So it is real and odd. So the Fourier transform is real and odd. Now we are going to tell about x of t. For that, we have a table like this, wherein in frequency domain, if it is real and odd, in time domain, it is imaginary and odd. So the answer is purely imaginary and odd function of time. This is very important for you guys to know. So for different type of signals in the input domain, what will be that signal in the frequency domain? That you can get from this table, and inverse also. Is the idea clear, guys? What is the Fourier transform of t e power minus mod t? So if I have t into x of t, what is the Fourier transform? So multiplication by t property we have to apply. Okay. So t into x of t, if I take Fourier transform, I'll be getting j into dx of j omega by d omega. So if you multiply by t in the time domain, in frequency domain, you have a differentiation that is involved. What is the general case of this? T power n into x of t, if I take the Fourier transform, I'm going to get j power n into d power n into x of j omega by d omega power n. So you're differentiating it n times. So if I multiply by t power n in the frequency domain, you're differentiating x of j omega n times. So for the first thing, for n is equal to 1, we have the proof here. This is the formula for Fourier transform. We are differentiating by omega. So d by d omega into x of j omega. So if we see the right side, only this term has omega. So if I differentiate this, I'm going to get minus jt into e power minus j omega t into x of t into dt. Correct? So if you look into this, This minus j, we can take it to the left hand side, right? And then you will have t into x of t e power minus j omega t dt. So, Fourier transform of this is this. Okay. So, using this, for e power minus a mod t, we know the Fourier transform is 2a by a square plus omega square. We saw this last week. So the Fourier transform of e power minus a mod t is 2a by a square plus omega square. Now we are multiplying it by t and a is just 1. So multiplying by t, there I had j into d by d omega of this. So if I differentiate this 2 by 1 plus omega square, I am going to get minus 4j omega by 1 plus omega square the whole square. So the answer is D. Consider a system whose input x of t and output y of t have the following relationship between their Fourier transforms. So y of j omega and x of j omega has the following relation. So y by x is 2j omega plus 4 by 7 minus 2 omega square plus j omega. What would be the differential equation relation between x of t and y of t, where if you put this, it denotes differentiation. So how do we find this differential equation? From this, we have to find the relation between x of t and y of t. First step, what you guys have to do is bring this to this side, bring this to this side, construct a one line equation with x of j omega and y of j omega, and then we have to find the inverse Fourier transform of it, of that equation. Can you guys try this? Okay. So let us see how to solve this. I'm bringing this to the left hand side and this to the right hand side. So I have 7 plus, so minus 2 omega square. I'm writing it as plus 2 j omega the whole square plus j omega into y of j omega equals to 2j omega plus 4 into x of j omega. Now this expression, so we have taken y of j omega inside and x of j omega inside. For this we are finding the inverse Fourier transform. So for the entire expression we are finding the inverse Fourier transform. So y of j omega's inverse Fourier transform is what? Y of t. So 7 into y of t plus 2 into, we have j omega square into y of j omega. So this inverse Fourier transform is y double dash of t, right? Plus j omega into y of j omega. So it is y dash of t equals to 2x dash of t plus 4 into x of t. So the answer is B. So the basic property what you guys used is dx by dt's Fourier transform is j omega into x of j omega. So the answer is B. I'm moving on to the next question. If y of j omega is x of j omega into h of j omega, then what can we tell about y of t, x of t and h of t? So in the frequency domain, if x and y are products of each other, then in time domain, what will they be? Correct. So there it's going to be convolution. So if I have x of t convolved with h of t in the time domain, if I take Fourier transform, it's going to be x of j omega into h of j omega. So if I have to do this difficult convolution operator in the time domain, what I can do is I can take Fourier transform of x of t, I can take Fourier transform of h of t, and I can just do product. So instead of doing convolution in the time domain, we can do product in the frequency domain. So the explanation for this convolution property is given here. So basically we start with x1 of t convolved with x2 of t. Okay, you write the formula for convolution and then you will do some variable translation and then we can get to the answer. So you guys can check this out. I will be uploading this presentation so you guys can have a look how we got this. So the solution is B. Y of t is x of t convolved with h of t. Okay. Determine the Fourier transform of the following figure. So an x of t is given to us. How do we find the Fourier transform for this x of t? One way is directly trying to find the Fourier transform, and there's another way. So if I have dx by dt, What is the Fourier transform, guys? Yeah, j omega into x of j omega, right? So, what if I differentiate this x of t? So, what I'll get if I differentiate this x of t, x dash of t, I will be getting this one impulse here, one impulse here, and here it's nothing, so it's just there's no change, so this will be just 0, and then you have another impulse here, and then you have another impulse. So you just have 4 impulses. Now can you use this and find the Fourier transform, guys? Okay. So for each impulse, we can write the Fourier transform, and then you can solve them. So if you solve, finally you will be getting, so this is y of j omega. Now you have j omega into x of j omega. So you divide by j omega. So you'll be getting this answer. So the answer is B. Sorry. Similar way, you have to determine the Fourier transform of this figure. So what is our x of t? X of t is minus t from -1 to 1. So put that in limits and then we try to solve it. So it's this, you have to solve it using this. So integral u dv, we can write it as uv minus integral v d. So use this and then if you solve, we can get to the answer. The answer is D. So yes, so we are done with the questions. Now let us see what we're going to do in Octave. In last week's session, we saw that the function to perform Fourier transform was Fourier of f. Now, what is the function to perform inverse Fourier transform in Octave? It is I Fourier of f. Okay, so if you write Fourier of f, basically first it gives us the Fourier transform, and then there is something called simplify. So this function simplifies the answer for us, and then if I take this answer and then if I find I Fourier, and then again if I do simplify, I'm going to end up with the same thing. I'm going to end up with the same thing. So sine of 3t by pi t was our input. Now we got sine of 3x by pi x. Okay, then we can end the session for today. Thank you all.